Welcome to all of you. Now we discuss about the MCQ of the question paper Linear Programming Problem 2021 Semester 5 CBCS B.Sc Honors in Mathematics. Question paper 2021 Question 1a. Let X be the set of all order pairs xy such that x square plus y square equal to 1 and y is the set of all convex combinations of the vertices of a cube. Then the correct option is this x, capital X, this is capital X, and this is capital Y. Capital X is not a convex polyhedron, but capital Y is convex polyhedron. The answer now, first we define the convex rule for this. The set of all convex combinations of a given set of points X constitutes a convex rule of X and is denoted by Cx. Cx is the smallest convex set containing set of points X. And convex polyhedron, the set of all convex combinations of a finite number of points, is called convex polyhedron generated by these points. All convex polyhedron is a convex rule, but not vice versa. Now, consider the example. First example, this capital X is the set of all those orders pair xy, x square plus y square equal to 1. So, this is the set of all points on the circumference of the unit circle centered at origin. This capital X is a set of all points lying on the boundary of the unit circle. In the circle with its interior, including boundary, its convex rule Cx. So Cx is the convex rule, is a set of all order pairs such that x square plus y square less than equal to 1. Now this is a cube. This consider this is a cube. The whole cube is the convex rule of the set of points consisting of only the 8 vertices of the cube in E3. So they are A, B, C, D, E, F, G, H. 8 vertices of the cube E3. Clearly, the convex rule of 8 vertices of cube is a convex polyhedron. But the above circle with interior points is not a convex polyhedron, and as it has infinite number of extreme points. So the correct option is capital X is not convex polyhedron, but capital Y is a convex polyhedron. Next question. The number of extreme points of the convex set this S such that mod x less than equal to 1, mod y less than equal to 1. Correct option is 4, 3. Here mod x less than equal to 1 means this minus 1 less than equal to x less than equal to 1. So this is the E2 plane, this x-axis, y-axis, this is the x equal to minus 1, this line segment, and this x equal to plus 1, and this mod y less than equal to 1, this means y equal to 1 and 1 equal to minus 1. So we get a square including interior points and boundary points. Here the 4 vertices A, B, C, D, minus 1, 1, 1, minus 1, 1, 1, and D, minus 1, 1. The extreme point is the point X is an extreme point of a convex set S if and only if there do not exist point x1, x2, x1 not equal to x2 in the set S such that x equal to lambda x2 plus 1 minus lambda x1, 0 less than lambda less than 1. Also, lambda not equal to 0 and lambda not equal to 1, so that x1 and x2 are both different from x. That is, if a point x belongs to S does not lie on the line segment joining any two points x1, x2 other than x in the set. So here this A, B, C, D are corner points are the extreme points of these four extreme points here. Any point on the circumference of a circle is an extreme point of the convex set of points within and on the circle, and the vertices of polygon are the extreme points of the convex set of points within and on the boundaries of the polygon. All extreme points are boundary points of a set S, but not vice versa. All boundary points may not be an extreme point. So correct option is 3. Number of extreme points here 4. Question C, for the system of equations this and this, x1 equal to 3 by 2, x2 equal to 0, x3 equal to 0 is correct option is basic feasible but degenerate solution. Basic feasible but degenerate solution. The given system of equations can be written as in matrix form. This 2 minus 1 3 minus 6 3 7 and 2 by 3 matrix, and this is the column matrix x1 x2 x3, and this is the constant terms column matrix 2 by 1, or this a1 x1 plus a2 x2 plus a3 x3 equal to b, where a1 is the column matrix 2 minus 6, a2 is the minus 1 second column minus 1 3, and a3 is the 3 7, and b is the this constant value terms 3 minus 9 column matrix. Now here x2 0 x3 0, so maximum number of linearly independent vectors is here 2, because there are 2 rows. So here if we choose this x2 equal to 0 non-basic variable, so first we choose x3 equal to 0. X3 is the non-basic variable, so x1 and x2 is basic variable. Then basis matrix b1 equal to a1 a2. First we choose b1 this, and then actually x1 and x2 are basic variables. But here determinant of b1 is 0, so a1 a2 are linearly dependent vectors. So we cannot find the basic solutions from these vectors, next we choose x2 is non-basic variable. So consider b2 matrix, basis matrix a1 a3. Now determinant of b2 not equal to 0. So a1 a3 are linearly independent vectors, and so x1 x3 are the basic variables and x2 is a non-basic variable. Since x3 equal to 0, here x3 equal to 0, basic variable is 0. So basic variable is 0. Hence the given solution is a degenerate basic feasible solution. Feasible means all non-negative. Non-negative solution. Basic variables are all non-negative. These are feasible solutions. So basic feasible but degenerate solution. Obviously, this solution satisfies the system. Correct option is 2 here. Next question D. Consider an LPP maximize z equal to cx subject to the constraint ax equal to b. And the correct option is 1. At least one index number is found to be negative and all elements in the column corresponding to negative index are non-positive. And then the problem admits an unbounded solution. This is the condition for unboundedness. Now, we know if at any iteration of the simplex algorithm, we have Zj minus Cj less than 0 for at least one index j, and for this j, yij less than equal to 0, that is all elements in that column are non-positive. For all I equal to 1 to m, then the LPP admits an unbounded solution in a maximization problem. So obviously, correct option is 1. And for minimization problem, Zj minus Cj greater than equal to 0 for at least one j, and Yij less than equal to 0 for all I. Question E. Z equal to this 20x1 plus 9x2 subject to this constant this. The minimum value of Z is what? 2x1 plus 2x2 greater than equal to 36, 6x1 plus x2 greater than equal to 60, x1 greater than equal to 0, x2 greater than equal to 0. First, we solve this problem graphically. So first we draw this line 2x plus 2x2 equal to 36. So x1 by 18 plus x2 by 18 equal to 1. So this x1 axis, this x2 axis, this x1 by 18, 18, 18. So this is greater than equal to. So obviously in this direction, opposite to origin. And for this straight line, 6x1 plus x2 equal to 60. So x1 by 10 plus x2 by 60 equal to 1. So we get this line also is greater than equal to inequality. So a region opposite to the origin of the straight line. So our feasible region is this shaded region of the figure indicates the feasible region with corner points here. This point A 0, 6, 60, B intersecting point, and solving this 1 and 2 we get x1 equal to 42 by 5, x2 equal to 48 by 5, and C is 18, 0. So values of the objective function z at these corner points, we get ZA, objective function z at the point A is 540, ZB is that 250.54.4, and ZC equal to 360. So minimum value is objective function occurs at the point B, intersecting point. So there is no correct option here. So actually wrong answers are all these. Question A. In solving the LPP, minimize Z equal to this, subject to this. Redundant constant are what? Correct answer is 2. If we draw for this straight line 2x plus y equal to 10, so this is the 2x plus y equal to 10, this is greater than equal to 10. So region in this direction, opposite to the origin, and x1 greater than equal to 6, this x1 equal to 6, greater than equal to 6, and y greater than equal to 2, y equal to 2 this, y greater than equal to 2, so region is this, and this x greater than 0, y greater than 0, so this is the first quadrant. So combining all these, we get the feasible region as the shaded region here. Obviously, we observe from this figure that this inequality 2x plus y greater than equal to 10 and x greater than equal to 0, that is the y-axis, and this region right hand side of the y-axis and the upper side of the x-axis y greater than equal to 0. Obviously, redundant constraint. We can remove this constraint and has no effect on the shaded region. So correct option is 2. A degenerate basic feasible solution in a balanced TP with M origins and N destinations will consist of, correct option is this 4. Now, the number of basic variables in a transportation problem is at most M plus N minus 1. Hence, a non-degenerate basic feasible solution in a transportation problem will consist of at most M plus N minus 1 positive variables. The rest Mn minus bracket M plus N minus 1 variables being 0. Non-basic variables. This. So, a degenerate basic feasible solution in a TP will consist, degenerate means when at least one of the basic variable equal to 0. So, basic number of basic variables at most is M plus N minus 1. So, M plus N minus 1 is the uh, at most M plus N minus 2, the number of positive variables at most when mm, mm, at least one of the basic variables is equal to 0 for a degenerate basic feasible solution in a transportation problem. Question 8. The assignment problem will have alternate solutions when alternate solution when there is a tie between zero opportunity cost cell. Option 3. This is a situation when exactly one zero cannot be found either in a row or in a column. Then this indicates that there exists an alternative optimal solution of the assignment problem. So correct option is 3. Question I. Consider the game with P of matrix this: player A maximizing player and player B minimizing player. P7 3 minus 2 P minus 8 minus 3 4 P. The value of P for which the game is strictly determinable satisfies, correct option is 3. Minus 2 less than equal to P less than 3. First we ignore the value P and calculate the row minimum. So first row minimum is 3. For second row minimum is minus 8. And for third row minimum is minus 3, ignoring the value of P. And then we calculate column maximum. For first column maximum is minus 2. For second column maximum is 7. For third column maximum is 3. Now find the new lower bar, that is the maximum value. So maximum of row minimum, this is 3. And minimum of column maximum, this is minus 2. This is new upper bar. This is called minimax value for P. So for strictly determinable game, the value of the game new, obviously minus 2 less than equal to new less than equal to 3. And then value of the P is also minus 2 less than equal to P less than equal to 3. Hence correct option is 3. Question J. Consider the following pair of matrix of the game. Identify the dominance in it. dominance in it. Correct option is 2. Y dominates Z. Because here all elements of the yth column, here the yth column 7, 6 and 2, that is the second column, actually second column, be greater than or equal to, here all elements are greater than or equal to, greater than of the corresponding elements of the gth column, that is the third column. So 7 is greater than 3, 6 is greater than 4, 2 is greater than 0. So obviously second column dominates the third column. So y dominates z. Then by dominance property, we discard the yth column. Thank you. This completes the multiple choice question 2021.